Hello, my dear students. Welcome to the session continuation of important observations from power electronics concepts. In this session, with respect to module 4 inverters, that is DC to AC converters, I would like to discuss about single phase bridge inverters, three phase bridge inverters, current source inverters, and PWM techniques. All of you concentrate. First, we have to start with inverter. Friends, what is the inverter? The static power electronic circuit which converts DC to AC at variable voltage, variable frequency and variable number of phases. That is, in inverters at output side, we can control the voltage, we can control the frequency, we can also control the number of phases. Sir, what do you mean by controlling the number of phases at output side? DC to single phase AC we can convert, DC to three phase AC also we can convert. That is the meaning of controlling the number of phases at the output side. These are the some introduction points with respect to inverters that you have to concentrate. How to get the DC supply in inverters? What is the DC link inverter? All these points that you have to concentrate. And what type of switches we have to use? What exactly a single phase inverters, three phase inverters, for a high power application, which inverters we have to use, for low power application, which inverters we have to use. All these observations are important. If you use the BJT, MOSFET, IGBT, GT1 SIT, other switches, no need of any commutation circuits. If you use the thyristors or the switches, then external commutation circuit is required. All these points that you have to consider. And what the classification of inverters? In general, inverters are classified into line commutated inverter and force commutated inverter. But point you have to remember, friends, inverter is nothing but a force commutated inverter only. It is given line commutated inverter, then only you take the line commutated inverter. I told already, line commutated inverter actually is not an inverter circuit, it is a rectifier circuit. No? Rectifier alpha greater than 90 degrees. Full wave rectifier alpha greater than 90 degrees acts as the inverter. Those inverters are called line commutated inverter. But here study of inverters are nothing but a study of forced commutated inverter. That is, a full wave rectifier alpha greater than 90 degrees acts as inverter. Those inverters are called line commutated inverter. What exactly forced commutated inverters? In the forced commutated inverters, we have to use some external circuits are required to turn off the device at right moment. This is called forced commutation circuit. Types of forced commutated inverters. If the input is voltage source, those inverters are called voltage source inverter. That is called voltage fed inverter. If the input is current source, those inverters are called current source inverter. That is also called current fed inverter. But you have the doubt here, sir. If it is not given voltage source inverter or current source inverter, simply they given inverter. Then which inverter you have to take? Simply they given inverter means you take the voltage source inverter. For example, if they given the circuit now, then how to identify? Is it a voltage source inverter or current source inverter? If input is voltage source, then it is voltage source inverter. If the input is current source or voltage source in series with large inductor, the input is current source or voltage source in series with large inductor. That is equivalent to current source. Those inverters are nothing but a current source inverter. Circuit is not given. Simply they given inverter means you take the voltage source inverter. Based on the nature of output voltage waveform, the inverters are square wave inverters, quasi square wave inverter, pulse width modulated inverter. Based on the type of configuration, bridge inverter, series inverter, parallel inverter, McMurray inverters. Based on output number of phases, single phase inverters, three phase inverters. But if you see the gate silvers, mainly in the gate silvers, bridge inverters they given. In that bridge inverters, single phase bridge inverter they given, three phase bridge inverter. And one more topic is a PWM technique, pulse width modulation technique. That is also very important. That is, once you are preparing inverter concept mainly for gate point of view, mainly you have to concentrate single phase bridge inverters, three phase bridge inverters and PWM techniques. Finally, you have to concentrate on current source inverter. So these are the classification of inverter. And one more important repeated model of question in gate exam. This is very important. Sometimes by giving the circuit, by giving the some equivalent circuits, uh, by giving some devices, which of the following devices are used for the CSI, which of the following devices are used for VSI, that type of questions are it is framed. But point to remember, in VSI, unipolarity bidirectional switches are used. For a given switches, You have to draw the ideal characteristics. The switch which satisfy the unipolarity bidirectional. Unipolarity bidirectional. Those switches are used for the VSI. And what type of switches are used for CSI? See the difference between VSI and CSI. Let us view the detailed differences also. In voltage source inverter, input is voltage source. Internally, it consists of parallel capacitors. In current source inverter, input is current source or a voltage source in series with large inductors. This concept already you studied even in network theory also. A voltage source in series with large inductor is equivalent to current source. Sometimes they will give the voltage source with inductor, that is also current source, or directly they will give the current source. Then what type of switches are used for the current source inverter? The switches which having the bipolarity capability. That means which blocks the both the polarity but conducts only in one direction. Conducts in only one direction. Those switches are used for the current source inverters or current fed inverter. That you have to concentrate. Then very important, the questions are asking which of the following devices are used for VSI, which of the following devices are used for CSI. If that type of questions are asked for given devices, you have to draw the ideal characteristics. The devices which satisfies bidirectional capability, those devices are used for VSI. The devices which satisfy bipolarity capability, those devices are used for CSI. Like that you have to identify. These are the some of the applications of the inverter that you have to concentrate. Where we can use these inverters, domestic application, industrial application. Then these are the applications of the inverters. But mainly for gate point of view, application point of view, not that much of important, but you have to concentrate. And one more very important topic that you have to concentrate. What are the differences between the voltage source inverter and current source inverter? In voltage source inverter, input is voltage source. Internally, it is having the parallel capacitor. In current source inverter, input is current source in series with a large inductor. Input is stiff or constant voltage source. Input is stiff or constant current source. Voltage source inverter is fed from a DC voltage source having small or negligible input. That is, in voltage source inverter, the input impedance is very small. In current source inverter, because of the series inductor, it is having the high input impedance. DC source is in parallel with a large capacitor, but VSI can be converted into CSI by connecting a large series inductor. It is having the large series inductor. Amplitude and waveform of output voltage is independent of the load. Important. In voltage source inverter, voltage is independent, but which is dependent? Current is dependent. In current source inverter, current is independent, but which is dependent? Voltage. Amplitude and waveform of output current is independent of the load. In current source inverter, output current is independent of the load, but voltage depends on the load. In voltage source inverter, voltage is independent of the load, but current is depends on the load. The waveform of the load current as well as its magnitude depends upon the nature. Here you see, voltage is independent, current is dependent. Here current is independent, voltage is dependent. This is some differences between voltage source inverter and current source inverter. This is the explanation, not required, but mainly you have to remember these points. VSI requires feedback diodes, but CSI does not require them. That is, in voltage source inverter, no need of any. In voltage source inverter, feedback diodes are required. But in current source inverter, no need of any feedback diodes. Every point is important. Already questions are framed in computer exam. Where we can use voltage source inverters. Voltage source inverters are used with less input impedance and high output impedance. But these are used with high input impedance and less output. VSI has slow response than CSI. CSI has fast response. Current source inverters are fast response. The commutation circuit is complicated. It uses current commutation. But in the case of current source inverter, the commutation circuit is simple. It contains only capacitor. It uses voltage commutation. The differences mainly have to right? The devices with bidirectional current capability used as main switches. The devices with bipolarity capability is used as switches. It's a bidirectional. Both the direction it is conducting. That switches are used as that devices are used as switches in voltage source. It is not used for regenerative application, but it is used for regenerative application. It is used for multi-drive control. It is used for single drive control. more favorable for inductive loads. These are more favorable for capacitor. Okay, these are the differences between voltage source inverter and current. But don't neglect this concept, friends. This is also one of the 5-star concept for your exam point of view. Please practice this. What are the differences between VSI and CSI? And this practice questions you have to practice. A constant current source inverter supplies 20 amperes to a load resistance of 1 ohm. If the load resistance is changed to 5 ohm, then the load current is. In current source inverter, current is independent of the load. Now, even though load is changed, current remains same. Initially, current is 20 ampere, resistance is 1 ohm, voltage is 20 volts. Now, resistance is 5 ohms. Now, current is remains same. 5 into 20, 100 volts. That is, there is no change in the current, only voltage will change. That is, current remains same, but voltage is becomes 100 volts. A constant voltage source inverter supplying load voltage of 100 volts for a load of 5 ohms. If the load was changed to 10 ohms, calculate the V0 and I0. Given is constant voltage source. In voltage source inverter, whatever the load you can connect, voltage remains constant. But initially the current is 20 amperes, now the current is 10 amperes. That is, in voltage source inverter, based on the load, current only changing, but voltage remains same. This is about the questions based on the differences between VSI and CSI. First, we have to start with one more important topic: single phase bridge inverters. A single phase bridge inverters are again single phase half bridge inverter and single phase full bridge inverter. The single phase half bridge inverter and single phase full bridge inverter. Mainly in single phase half bridge inverter, what type of switches we can use? Generally, MOSFET, IGBT, BJT, GTO, SCR is used. For a high power, high frequency application, MOSFET. For high power application, SCR we have. But I told already, input is voltage source. That's why it's voltage source inverter. In half bridge inverter, how many switches and how many diodes? Two switches. And just remember the configuration. Two switches and two diodes. Two switches and two diodes is the half bridge inverter. No need to concentrate on the operation. Final analysis is important. That is 0 to T by 2, S1 is on. T by 2 to T, S2 is on. This is the output voltage we can get. V0 equal to Vs by 2. V0 equal to minus Vs by 2. Then by drawing the waveform. This is important observation. For our load, voltage and current waveforms are same. What is the voltage waveform? Square wave. What is the current waveform? Also square wave. Except our load, this voltage source inverter requires the feedback. I told already, in voltage source inverter, feedback diodes are required. But in our load, no need of any feedback. But the purpose of feedback diodes is to carry the energy stored in the inductor and the capacitor. But in the case of resistive, there is no any storage. That's the reason why in resistive loads there is no need of any feedback diodes. Only for inductive and capacitive loads only feedback diodes are required. Then what is the operation? What is the operation for L load? But no need to concentrate on the L load. But very important is this one. In L load, in voltage source inverter, output voltage waveform is independent of the load. Whatever the load you can connect, voltage waveform, output voltage waveform is always square wave. Let us assume that it is a square wave inverter. But based on the current, which waveform will change? Current wave. Based on the load, which waveform will change? Current waveform will change. Based on the load, current waveform will change. Then, in purely inductive load, what is the current waveform? Triangular. Very important. In voltage source inverter, purely inductive load, current waveform is triangular. These observations are important. For lagging power factor loads, if they ask what is the sequence of conduction of devices, first to start with diode, next switch. First to diode, next switch. Diode switch. Simply remember, for lagging power factor loads means inductive loads. For lagging power factor loads means inductive loads. If it is inductive loads, if any question is asked, what is the sequence of conduction of device? Not only pure L load. If there is an inductive nature, then first diode, next switch will conduct. For leading power factor loads, you have to take like this. First switch, next diode. S1, D1, S2, D2. It is a half bridge inverter. Na? At a time, only one device is conducting. The only difference between half bridge and full bridge is all are analysis, all are same. Only difference is in the case of half bridge inverter, 3-wire DC supply. At a time, one switch is conducting. In full bridge, 2-wire DC supply. At a time, two switches will conduct. Two devices will conduct. This is for inductive loads, 5-star concept. Single phase half bridge inverter, purely inductive load. For the output voltage waveform, square wave. For the output current waveform, triangular wave. Each device conduction time is how much? T by 4 or 90 degrees. Time taken to reach the peak value is how much? T by 4. Very important. That is, for purely inductive load, how much time is taken to reach the peak current? I am not asking peak to peak. Peak to peak is T by 2. Peak current is, to reach the peak current is T by 4. Once you know this one, you have to calculate what the peak value of current. In the case of purely inductive load, the peak value of current equal to VL by 4F. Very important. Repeated question in the GATE exam. The purely inductive load, what is the peak current expression? VL by 4FL. What the peak to peak current, it is asked 2 times of the peak current. Peak to peak current is 2 times of the peak current. This is for purely inductive. Then waveforms for other loads. If RL load is given, this is the waveform. If RLC, XL greater than XC. XL greater than XC means inductive. Inductive means current is lagging. XC greater than XL means leading, capacitive, current is leading. But point to remember, students, it is RL load na, lagging. First diode, next switch, diode switch, diode switch. It is also lagging current na, lagging current I told already, diode switch will conduct. This is which one? Leading loads na. Leading loads means first switch, next diode, first switch, next diode. Okay, this one. That is, this also very important. For XL greater than XC, the circuit is what nature? For XL greater than XC, circuit is overdamped. Then which commutation we can use? Forced commutation. For XC greater than XL, circuit is underdamped. Circuit is underdamped. What type of commutation we can use? Load commutation we have to use. These points are very important. Then for purely resistive load, you have to write this formula. Very important. This is the analysis points. For purely resistive load, there is no conduction of the feedback diodes. I told already, resistive loads, feedback diodes will not conduct. That's why by giving the resistive load, it is asked what is the average diode current, what is the RMS diode currents, equal to 0. Resistive loads, the diodes will not conduct. That's why average diode current and RMS diode currents are equal to 0. For this resistive load, what the RMS value of fundamental component? I01 equal V01 by R. What is the V01? It is a RMS value of fundamental voltage. That later on we will do proof also. This is for half bridge inverter. RMS value of fundamental voltage equal to root 2 Vs by pi. Once you know the V01, like this you have to calculate I01. Then this is about the maximum value of current. This is the average switch current. That is S1 current, RMS switch current. But diode currents are equal. That is the diode currents are 0 because of resistive load. Feedback diodes will not connect. RLC load XL greater than XC. RLC XL greater than XC means the circuit is which one? Overdamped. What type of commutation? Forced commutation we can use. In this case, the switches will conduct, diodes also conduct. It is a inductive loads na. XL greater than XC means inductive nature. Inductive nature means first diode, next switch. Diode switch it will conduct. Now these formulas you have to practice. Still now in GATE exam based on these formulas, no questions, but it is the expected model of questions, friends. You have to calculate I01 equal V01 by Z1. What the average value of each switch current or thyristor current you have to calculate. What the RMS value of each switch current? Direct formulas you have to remember. What the average value of each diode current? What the RMS value of each diode current also you have to calculate. How to calculate theta here? Theta equal to tan inverse XL minus XC by R. Because XL greater than XC na, that's why you take XL minus XC by R. If XC greater than XL, you take the XC minus XL by R. These are the calculation of fundamental RMS current. This is the average value of switch current. This is the RMS value of switch current formula. RMS value of switch current. Please concentrate this formula. It is very important. This is expected for 2 marks. What the average value of diode current? What is the RMS value of diode current? This is for RLC. This is for RLC XC greater than XL. RLC XC greater than XL. You need to concentrate on the waveform. This you have to take. Then RMS value of fundamental output current equal to V01 by Z1. Average value of fundamental source current equal to, this is the formula you have to apply. Power delivered by the each source equal to Vs by 2 into Is. Vs by 2 into Is. That you have to concentrate. Then these are the note points. What is the purpose of using the feedback diodes for inductive loads? Feedback diodes carries energy stored in the reactive elements and delivered to the source, and some energy is dissipated in the resistor. For the purpose of using feedback diodes, it carries the energy stored in the reactive elements, and that some energy is delivered to the source and some energy is dissipated in the resistance. During the conduction of feedback diodes, only corresponding switches are reverse biased. For example, uh, D1 is conducting, S1 is reverse biased. D2 is conducting, S2 is reverse biased. Only corresponding switches are reverse biased. That's the reason why diode conduction time is taken as a circuit turn-off time. So diode conduction time taken as a circuit turn-off. For example, if they given diode conduction angles are theta, very important. In bridge inverters, diode conduction time is taken as a circuit turn-off. In a bridge inverter, theta is the diode conduction angle. Then how to define the circuit turn-off time? Circuit turn-off time equal theta by omega. If theta is the diode conduction angle, what are the main switch conduction angles, friends? Pi minus theta. Very important formulas. This is very important formulas. Theta is the diode conduction angle. Then how to calculate the circuit turn-off time? Theta by omega. What is the main switch conduction angle? Pi minus theta. Once you know the angle, how to calculate the time? Divided by omega. Once you know the angle, calculate the time divided by omega. Yeah, this question you have to practice. Very, very important for your exam point of view. You please practice this one. If you don't have the time to practice all these formulas, minimum try to practice these models of question. This is R equal 2 ohms, XL equal to 8 ohms, XC equal 6 ohms. This is the case of XL greater than XC. If XL greater than XC, what is the RMS value of diode current formula you know? Use that one. We can also expect what is the average value of diode. But point to remember, here fundamental voltage directly given. Sometimes they don't give the fundamental voltage. If they don't give the fundamental voltage, how to calculate the fundamental voltage? This is which inverter? Half bridge inverter. Na? In half bridge inverter, fundamental voltage equal to root 2 Vs by pi. But directly fundamental voltage is given. Directly that I will take it. Sometimes they don't give fundamental voltage. They will give the supply voltage. Then you have to use this for half bridge inverter. Then I calculated RMS value of diode current. This finally I got this is the I naught one. Once you know the I naught one, the RMS value of diode current is 17.3 amp. If they ask what is the circuit turn off time? Circuit turn off time I told already. Diode conduction time is nothing but a circuit turn off time. Then diode conduction angle by omega gives the circuit turn. Each switch conduction angle. Once theta is the diode conduction angle, what is each switch conduction angle? Pi minus theta. Like this you have to practice this model of question. Next, operation and analysis of single phase full bridge inverter. In half bridge inverter, how many switches and how many diodes? Two switches and two diodes. But here four switches and four diodes. In the case of full bridge inverter, there is exists a four switches and four diodes. That is, it is combination of two half bridge inverter. This is one half bridge inverter. This is one half bridge inverter. That's why it is a combination of two half bridge inverters. Then the only difference is number of devices are different. But here supply voltage is Vs now. That is how many wire supply here? Two wire DC supply. If you see the half bridge inverter, friends, if you see the half bridge inverter, how many wire supply here? It is a 3-wire DC supply. In half bridge inverter, it is a 3-wire DC supply that you have to concentrate. This is 1, 2, 3. 3-wire DC supply. But in the case of full bridge inverter, it is a 2-wire DC supply. So that is also one of the main difference between half bridge and full bridge inverter that you have to concentrate. But it is a combination of two half bridge inverter. Remaining points as it is. But in the case of half bridge inverter, output voltage is Vs by 2. But here output voltage equal to Vs we can get. Half bridge inverter, Vs by 2, here Vs. That's the reason why half bridge inverter efficiency is 50%. But here it is 100%. Then resistive load, what is the output current waveform, square waveform, output voltage and output current. There is no change. Remaining whatever the half bridge inverter waveforms I given, same waveforms it will repeat. But in a half bridge inverter it is Vs by 2, but here it is a Vs square. In a half bridge inverter at a time one switch is conducting, but here two switches are conducting. Then for purely inductive load same points. Each device conduction time is T by 4. For the peak current VL by 4FL. Output voltage is square waveform. What is the output current waveform for purely inductive load? It may be half bridge inverter or full bridge inverter, friends. That is output current waveform is triangular wave. But lagging power factor loads, first which devices will conduct? First diodes, next switches. But here at a time how many devices are conducting? Two devices are conducting. That is in lagging power factor loads, first diodes, next switches. For leading power factor loads, first switches, next diodes will conduct. Remaining as it is. And this quadrant operation also you have to concentrate. Actually, if S1, S2 is conducting, V naught positive, I naught positive, that's why it is the first quadrant. S3, S4 is conducting V naught negative, I naught negative, power is positive. But D1, D2 is conducting, power is negative. D3, D4 is conducting, power is negative. Power is negative. This observation is also important. In which quadrant S1, S2 will operate? In which quadrant S3, S4 will operate? In which quadrant D1, D2 will operate? In which quadrant D3, D4 will operate? That observation is also important concept. And these are the waveforms for different loads, RL loads, lagging loads. Lagging loads means first diode, next switches. XL greater than XC, it is also lagging, first diode, next switch. XC greater than XL, this is the leading, first switch, next diodes will conduct. These are the waveforms. And this for resistive load, how to do the analysis? The only difference is in half bridge inverter root 2 Vs by pi, but here 2 root 2 by pi into Vs. That is root 2 Vs by pi, but here it is a 2 times times. Then I01 you know, V01 by R. IS1 average value of each switch current, RMS value of each switch current, what the IM value, what the average value of diode current, RMS value. Here diode currents are 0 because resistive load, no need of any feedback diodes. Resistive load, no need of any feedback diodes. That you have to concentrate. For RLC XL greater than XC, this is for resistive load. Then RLC XL greater than XC, inductive loads, how to calculate I01, average value of switch current, RMS value of switch current, average value of diode current, RMS value of diode. These formulas you have to practice. To solve the problems based on this topic, these formulas you have to practice. Then RLC, XC greater than XL. XC greater than XL means leading power factor load. For leading power factor load, how to write the formulas? This is I01 formula. That is I01 is RMS value of fundamental output. RMS value of fundamental output. It is a full bridge inverter. 2 root 2 by pi into Vs, V01. If they don't give a V01 directly, you have to calculate V01 using that formula. Then what is the average source current? What is the power delivered by the source? What is the power delivered by the source? What is the average source current? What is the power delivered by each source? What is the circuit turn off time? Let us assume that theta is the diode conduction angle. If theta is the diode conduction angle, how to calculate the circuit turn off time? The circuit turn off time equal to theta by omega. If theta is the circuit, if theta is the diode conduction angle, what is each switch conduction angle? Pi minus theta. All the points are repeated here. Same points. In half bridge inverter, whatever the points are given, same points it is repeated that you have to concentrate. And this problem you have to solve. It is given resistive load. It is asking that RMS value of diode current. It's a very simple concept oriented question. It is given that resistive load. What the RMS value of diode current? No need to apply any formulas. We know that for resistive load, feedback diodes will not conduct. Then what is the RMS value of diode current equal to 0. Then this problem also you have to concentrate. This is the repeated model in gate exam. If they ask what is the peak current equal to VL by 4FL. If it is asked peak to peak current, you take the 2 times of this current. Peak to peak current is 2 times of this current. Peak current equal to VL by 4FL. This formula is for purely inductive load. What type of loads? Purely inductive load. Then what the sequence of conduction of devices for inductive loads? For inductive loads means first diodes, next switches. First diodes means start from this one. No need to by heart, start from this one. D1, opposite you take D2, S1, S2, D3, D4, S3, S4, D1, D2, S1, S2, D3, D4, S3, S4. Because it's the inductive loads now. If it is a capacitive loads, it is given. Lagging loads means, inductive loads means lagging loads. Lagging loads means first diodes, next switches. Leading loads means first switches, next diodes will conduct. That you have to concentrate. And here it is asking that V0 less than 0, I0 greater than 0. V0 less than 0 means voltage negative. Voltage negative, current positive. Voltage negative, current positive means fourth quadrant. Fourth quadrant, which devices will conduct? D3, D4 will conduct. Answer is D3. Like that you have. But if they given voltage less than 0, current greater than 0. Voltage less than 0, current greater than 0 means voltage negative, current positive. That is fourth quadrant. Fourth quadrant, which devices will conduct? D3, D4 will conduct. Yeah, that is one concept that you have to concentrate. Continuation of this. What is the Fourier analysis of single phase full bridge inverters? What is the Fourier analysis of single phase full bridge inverter? Up to now I explained only operation and analysis. Normal analysis of half bridge inverter and full bridge inverter. That is one concept. Then one more concept is Fourier analysis of single phase full bridge inverter. If you apply the Fourier analysis for single, why you have to apply Fourier analysis for single phase full bridge inverter? It is a square wave now. What the RMS value of output voltage equal to Vs. Then if you apply the Fourier analysis, there is some formulas that is very important. By applying the Fourier analysis, then this is the Bn value, A0 0, An is also 0. For a square waveform, if you apply the A0 is 0 you can get, An is also 0 you can get, Bn equal to 4 Vs by n pi. Then by substituting A0, An and Bn in this formula, finally we can get summation n equal to 135 up to infinity 4 Vs by n pi sin n. This is direct formula also you can expect in gate exam. That is, which is the most dominant harmonic at input side of the full bridge inverter, third harmonic. It consists of only which harmonics? Odd harmonics. Which harmonics are 0? All the even harmonics are 0. From this you write the so many formulas. Then how to write that formulas? This is the instantaneous value of output voltage of full bridge inverter. Summation n equal to 135 up to infinity 4 Vs by n pi sin n. Then it is the instantaneous output voltage. What is the maximum value of nth harmonic output without function? This is the maximum value of nth harmonic. How to find RMS value? Maximum value by root. This is the maximum value of nth harmonic. What is the maximum value of fundamental strength? If you have to calculate maximum value of fundamental, substitute n equal to 1, 4 Vs by pi. All these formulas for which one? Full bridge. If they ask the half bridge, easy to manipulate. Just here 2 we can get. Instead of 4 Vs, we can get 2 Vs. Because replace Vs by 2. That is for half bridge inverters. Once you remember the formulas for full bridge, no need to remember for half bridge. Just replace Vs by 2. Then what is the RMS value of nth harmonic output voltage? RMS value of nth harmonic output voltage equal to 2 root 2 by n pi into Vs. What is the maximum value of fundamental voltage? Maximum value of fundamental voltage equal to 4 Vs by pi. This is already given. What is the RMS value of fundamental voltage? Fundamental means in this formula you have to substitute n equal to 1. This is 5-star formula. Every formula is important based on this already questions. But this is very important. What is the RMS value of fundamental voltage of the full bridge inverter? 2 root 2 by pi into Vs, that is 0.9 Vs. Then what is the RMS output voltage? That is equal to Vs. What is the output power? V0 RMS. What is the fundamental output power? V0 1 square by R square. What is the distortion factor? Distortion factor equal to V0 1 by V0 R. For full, all these are full bridge, single phase full bridge inverter. Distortion factor equal to 0.9. What is the total harmonic distortion of single phase full bridge inverter? 48.43%. Up to now I calculated voltages. Then you have to calculate the currents also. For the instantaneous output current, just voltage divided by Zn. Voltage divided by Zn. What is the Zn here? Square root R square plus n into omega L minus 1 by n into omega C whole square. This is the theta n calculation that you have to concentrate. What is the maximum value of nth harmonic output current? Actually 4 Vs by n pi is the voltage. If you want current by Zn divided by Zn. Then what is the maximum value of fundamental output current? Replace n equal to 1. What is the RMS value of nth harmonic output current? This is the RMS value of nth harmonic output current. What is the RMS value of fundamental output current? This is the RMS value of fundamental current that you have to concentrate. But point to remember, for resistive load, nth order harmonic current equal to fundamental current by n. For inductive load, important observation. For inductive load, nth order harmonic current equal to fundamental current by n square. For capacitive load, nth order harmonic current equal to fundamental current. It is independent of harmonic. Very important. All this explanation for which inverter? Voltage source inverter. Voltage source inverter, capacitive loads, nth order harmonic current is independent of the order of harmonic. Nth order harmonic current is independent of order of harmonic in the case of voltage source inverter, inductive load. Then for R load, I01 equal to V0 by 1 by R, P01 equal to I01 square. If it is a reactive loads, I01 equal, don't take V01 by R, you take V01 by Z1. Then what is the P01 equal to I01 into R? Like this you have to calculate. This RMS current you also calculate square root I01 square plus I03 square plus I05 square if you know the harmonic square. Then finally the output power equal to I0 RMS square into R you have. This is a Fourier analysis of a full bridge inverter for square wave output. If it is a quasi square wave output, this is the waveform. It is also for full bridge inverter. Previously I given for square wave. If it is a quasi square wave inverter, same formula 4 Vs by n pi. But extra this term we can get. Cos n pi by 6 we can get. In a quasi square waveform, extra which term we are getting cos n pi by 6. This is the instantaneous output voltage expression of that is Fourier analysis of that is quasi square wave output. Next, you have to see the Fourier analysis of the half bridge inverter. For the Fourier analysis of half bridge. I told already, just to remember full bridge inverter, just replace in single phase full bridge inverter formulas, replace Vs by Vs by 2. We can get the formulas of half bridge inverter. Where 2 Vs na, sorry, in full bridge inverter is 4 Vs na, but here 2 Vs. Just replacing Vs by 2, then we are getting 2 Vs by n. That is all the full bridge inverter formulas divided by 2. That gives the half bridge inverter formulas. All this we have to concentrate. The first one is what is the maximum value of nth harmonic output voltage, what is the RMS value of nth harmonic output voltage in half bridge. These are half bridge inverters. What is the maximum value of fundamental output voltage in half bridge inverter? What is the maximum value of that? Sometimes the formulas directly exhaust. What is the RMS value of fundamental voltage in the case of half bridge inverter? What is the total RMS voltage Vs by 2? What the distortion factor, friend? Distortion factor equal to V0 1 by V0 RMS. What the total harmonic distortion? 1 by distortion factor square minus 1 whole to the power of 1 by 2. Here also 48.43% half bridge inverter also. And this is the current expression of half bridge inverter that you have. Just in full bridge inverter formulas, replace Vs by 2 or all the full bridge inverter formulas divided by 2. Next, for the nth order harmonic current equal to friends. Nth order harmonic current, this one. For resistive load, nth order harmonic current equal to fundamental current by n. For inductive load, nth order harmonic current equal to fundamental current by n square. For capacitive loads, this is the voltage source inverter na. Capacitive load, nth order harmonic current is independent of the order of harmony. This is RMS value of fundamental output current. This is the fundamental output power. This is fundamental half bridge inverter. What is the fundamental output power? Then this is the total output power calculation that you have to consider. And finally, what are the differences between single phase half bridge inverter and single phase full bridge inverter? I told already 4 switches and 4 diodes, 2 switches and 2 diodes, 2 wire DC supply, 3 wire DC supply. Here V0 RMS equal to Vs, but here only Vs by 2, 100% efficiency, 50% efficiency, peak inverse voltage Vs. Here also peak inverse voltage Vs. What are the output power, students? V0 RMS square by R, but here V0 RMS means Vs. What is V0 RMS in full bridge inverter? Vs. But what is V0 RMS here? Vs by 2. If you substitute here, Vs square by 4R, but it is Vs square by R. This is as compared to half bridge inverter, power is 4 times. As compared to half bridge inverter, voltage is 2 times. High switching losses, less switching losses. This is the instantaneous output voltage for half bridge inverter and full bridge. That is, the output voltage of full bridge inverter is 2 times of output voltage of half bridge inverter. Power output of full bridge inverter is 4 times of the power output of half bridge inverter. Yeah, this problem you have to practice. A single phase full bridge inverter operating with a supply voltage of 40 volts and delivering power to a load of R equal 10 ohms. Then calculate RMS voltage, RMS value of fundamental output voltage, total power and fundamental output power, and distortion factor and total harmonic distortion. Yeah, this I given the solution. Please go through this one. This model of practice, the question is very important. How to calculate the RMS output? Full bridge inverter RMS output voltage is Vs. RMS value of fundamental voltage is 2 root 2 by pi into Vs. This is for full bridge inverters. Once you know the RMS value of fundamental voltage and RMS output, if they ask the total power, this you have to. Fundamental output power, you have to use the V0. Then distortion factor equal to V0 1 by V0. Yes. Total harmonic distortion equal to 1 by distortion factor minus 1. Solve the above problem using single phase half bridge inverter. The only difference I told in half bridge inverter, that is full bridge inverter Vs, but here it's Vs by 2. That is 2 root 2 by pi into Vs, but it is root 2 by pi into Vs. Remaining that you have to write V0 equal to V0 R square by R, V0 1 equal to V0 1 square by R, distortion factor equal to fundamental by total RMS. That you have. And these are the points mainly concentrated with respect to current source. Up to now, whatever the single phase bridge inverter I explained, that is the voltage source because input is voltage source. But in current source inverter, input is current source. Output current, waveform and amplitude independent of the load, only voltage depends on. That is in current source inverter, current is independent, voltage is dependent. What are the applications of current source inverter? Speed control of AC motors we have to use, induction heating applications, lagging wire compensation, synchronous motor starting also we have to use. And this is the current source inverter. This guy in current source inverter, for any load, no need of any feedback. I told already. Current source inverter, we don't use the feedback diodes. Only in voltage source inverter, inductive loads only feedback diodes are required. Input is voltage source in series with large inductor is a current source. Then if you operate this circuit in current source inverter, that is 0 to T by 2, T1, T2 is on, T by 2, T3, T4 is also. Then we can get the output like this. That is in current source inverter, current is independent of the load, but voltage is depends on the load. But point to remember, for resistive load, there is no change in voltage and current waveform. That is, resistive load output current is square wave, output voltage also square wave. That is, in current source inverter, for any load, output current waveform is fixed, but based on the load which voltage waveform. Then I am drawing the waveforms of purely capacitive load. This is important. In current source inverter for purely capacitive load, friends. Current source inverter purely capacitive load. Voltage waveform is triangular. See the difference. Voltage source inverter purely inductive load, current waveform is triangular. That is inductive load current concept, capacitive load voltage concept. That's why voltage is triangular wave. Output voltage is triangular. Input voltage is sweep signal or sawtooth waveform. Important. In current source inverter, input signal is sweep signal or sawtooth waveform. Then it is subjected to frequency of 2f. If this frequency is f, then input is subjected to a frequency of 2f. Input is subjected to frequency of 2f. That is important. In current source inverter, if the output frequency is f, if the output frequency is f, then input is subjected to a frequency of 2f. That you have to concentrate. That is time taken to reach the peak currents, T by 4. Then what is the peak voltage? In the case of current source inverter, in the case of voltage source inverter, we calculated the peak current, but here it is calculating the peak voltage, that is I by 4 FC. Peak voltage equal to I by 4 FC. In current source inverter, if output is 1 cycle, then input is subjected to 2 cycle. Hence, input frequency is 2f in current source inverter. Point to remember, this is important observation. Purely inductive load, voltage source inverter, current source inverter. Purely inductive load, output current waveform is triangular. What is that peak current? VL by 4f. Purely capacitive load, output voltage waveform is triangular in current source inverter. What is the peak voltage? I by 4 FC. That is, current source inverters are more preferable for which loads, friends? Current source inverters are more preferable for capacitive loads. That you have to consider. Then what is the Fourier analysis of single phase current source inverter? This is the Fourier analysis of single phase current source inverter. First, I am calculating the current expression. That is, in voltage source inverter, voltage expression we calculated, but in current source inverter, current expression we calculated. Summation n equal to 135 up to infinity 4i by n pi into sin n omega. Now, this is the instantaneous output current. This is the instantaneous output voltage. In current source inverter, this is the instantaneous output current, instantaneous output voltage. Then you write any formula. In purely resistive load, nth harmonic output voltage equal to fundamental by n. Even for voltage source inverter also, nth order harmonic current equal to fundamental current by n. That is, there is here also 1 by n, in voltage source also 1 by n. Purely inductive load, this is different now. In purely inductive load, in voltage source inverter, fundamental current by n square. But here, nth order harmonic voltage equal to fundamental voltage. That is, in current source inverter, purely inductive loads, harmonic voltage independent of the order of harmonic. But capacitive load, it is a V1 not 1 by. But in voltage source inverter, capacitive loads, nth order harmonic current equal to fundamental. But here nth order harmonic voltage equal to fundamental voltage by n square. That points you have to concentrate. Yes. A single phase current source inverter supplying purely capacitive load operating in a square wave mode. The shape of the output current and voltage respectively. The shape of the output current and voltage respectively. What is the shape of the square wave and triangular wave? This is for purely capacitive load, square wave, and that is voltage is the shape of the output current and voltage. Output current is square wave in current source inverter, but output voltage is the triangular. And this problem also you have to practice with respect to current source inverter. These are the some important. This also one of the current source inverter. This also one of the current source inverter. That is single phase parallel capacitor commutated current source inverter. Single phase capacitor commutated current source inverter with R loads. Capacitor. For this case, mainly you have to remember the circuit turn off time. All this not. This is one formula you have to remember. Circuit turn off. single phase capacitor commutated current source inverter. Turn off time equal to RC into ln of 2 by 1 plus e power minus t by 2 RC. Approximate formula equal to RC into ln of 2. RC into ln of 2 is the approximate formula. These are the design considerations, no need to concentrate, but circuit turn off time, this load current expression mainly how to concentrate. Remaining these points, no need to concentrate. These are design considerations of a current source inverter, that is a capacitor commutated current source inverter. Then square wave current. To get the square wave current in this inverter, what the design consideration? To get the square wave current in these inverters, what the design consideration that you have to concentrate. What the maximum frequency of operation? The maximum frequency of operation equal to 1 by 10 RC. This also equal to 0.069 by TQ. Then to get the sinusoidal wave output in the case of current source inverter, what condition must be satisfied? These are the design considerations that you have to concentrate. How to select the capacitance value, how to calculate this XC at 3 times of the F minima. All these observations are very important. These are the design considerations. But in this case, in the total explanation of this is the parallel capacitor, this is a parallel capacitor commutated current source inverter. The only important, main important formula is this two. There's a load current expression and circuit turn off time is load current circuit turn off. And this one time it is framed in gate exam. That is a single phase auto sequential commutated inverter. Very important is in a single phase auto sequential commutated inverter, what the maximum frequency of operation? 1 by tau minima. Tau minima equal to 1 by 4 time constant. What the tau equal to R into C equivalent. The time constant equal to R into C equivalent. This you substitute here, we can get the maximum frequency of operation. That we can get the maximum frequency of operation. Next concept is performance parameters of the inverter. In performance parameters of inverter, there is so many. That is a given inverter is a good inverter. To analyze the quality of the inverter, to analyze the quality of the inverter, it is a good inverter or bad inverter. To analyze the quality, we have to use some performance parameters. Harmonic factor of nth harmonic factor, nth harmonic factor of nth harmonic, HFN. Yeah, this is one of the performance parameters of the inverter. This will use the RMS value of the nth harmonic voltage to the RMS value of fundamental voltage. It indicates the individual harmonic content. HFN equal V0 n by V0. This formula you have to remember. Next, what is the total harmonic distortion? Total harmonic distortion, this is the formula. That is RMS value of harmonic voltage by RMS value of fundamental voltage. These formulas directly you can expect, or problems also expect based on these formulas that you have to concentrate. These are the performance parameters of inverter. And this is one more formula for total harmonic distortion that already you know. Total harmonic distortion is that it indicates the total content of the harmonic. Harmonic factor is individual harmonic content. How much first order, how much third order, how much fifth order, like that. But THD will give the total harmonic distortion. Total harmonic distortion. What is the distortion factor formula? That with respect to harmonics. With respect to harmonics, how to define the distortion factor? Yeah, this is the distortion factor of nth harmonic individual components. What is the distortion factor of nth order individual component that you have to concentrate? Then what is the low order harmonic? When the particular harmonic is said to be lowest order harmonic. Lowest order. When you don't consider the that particular harmonic is lowest order or not, how to consider? Yeah, this observation is important. That you have to concentrate. Then what are the types of voltage control techniques in inverters? External control techniques, internal control techniques. But external control technique is not important. Internal control techniques are important. But in external control technique, there is so many techniques are there. External control of AC output voltage, external control of DC input voltage. In external control of AC output voltage is using AC voltage control and series inverter. And this is the AC voltage control method that you have to concentrate using AC voltage control method. This is the series. This is not important for gate point off. Just I given some points. Please go through this one. Then this is the using the series inverter control. Then external control of DC input voltage. In external control of DC input voltage, these are the external control methods. All these are the external control methods. External control methods are not. What the advantage of external control method that you have to concentrate? External control of. Then what are the disadvantage of external control? What are the disadvantage of external control methods also that you have to consider? But very important is internal control of inverter. What do you mean by internal control of the inverter? Output voltage from an inverter can also be adjusted by controlling the on and off of the switches with the inverter itself. The most efficient method of doing this is pulse width modulation control using within an inverter. By controlling the on of the switches, we can control the output voltage, that is called pulse width modulation. Then what are the drawbacks of square wave inverter? In order to overcome these drawbacks of square wave inverter, then we go for the PWM techniques. That is, in square wave inverter, we cannot control the RMS value, we cannot control the RMS value of fundamental voltage, we cannot control the frequency. All these are the drawbacks. In order to overcome these drawbacks, then we go for the PWM technique. This square wave inverter is also called 180-degree inverter. Square wave inverter is also called 180-degree. In pulse width modulation technique, by controlling the on time of the switches, we can control the output voltage. Then these are the advantages of the pulse width modulation technique. In pulse width modulation technique, point to remember, not only controlling the output voltage, we can also eliminate the specified harmonics. Not only controlling the output voltage, that is the main advantage of the pulse width modulation technique. Why do go for the pulse width modulation technique? Not only controlling the output voltage, we can also eliminate the harmonic. Yeah, this is the advantage. In pulse width modulation technique, single PWM technique, multiple PWM technique, sinusoidal PWM technique, trapezoidal PWM technique. Mainly single PWM, multiple PWM, sinusoidal PWM is very important. In a single pulse width modulation technique, number of pulses per half cycle equal to 1. Then what formulas mainly how to concentrate? All these not important. Mainly how to concentrate on the formulas. In a single PWM technique, what is the RMS value of fundamental? Sorry, what is the RMS output voltage? Not the fundamental voltage. This is the RMS output voltage. RMS output. The RMS output voltage is equal to Vs into 2D. Vs into square root 2D by. But point to remember, students, here pulse width is nothing but a 2D. But the pulse width is not 2D is nothing but a pulse width, not the D. In a single PWM technique, what is the pulse width? 2D is the pulse width, students. In a single PWM technique, 2D is the pulse width. Then what is the RMS output voltage? Vs into square root 2D by pi. 2D is nothing but a pulse width. In a single PWM technique, what is the pulse width? Is not D, it is a 2D. This formula is important. Then what is the harmonic analysis of a single PWM technique? That is a Fourier analysis. But in Fourier analysis, A0 is 0, An is also 0. This is the Bn value. Sometimes A0, An, Bn values also we can expect. That's why we have to concentrate. This exists only for odd harmonics, or all the even harmonics are 0. This is the instantaneous output voltage. From this, we have to write so many formulas. This is very important. Fourier analysis of single PWM technique is so many times it is asked in GATE exam. Then summation n equal to 135 up to infinity 4 Vs by n pi sin n pi by 2 sin n d sin n omega t. This is the output voltage, friends, that you have to consider. Then from this, you can write so many formulas. What the maximum value of nth harmonic output voltage? What the maximum value of fundamental? This is also very important. In a single PWM technique, what the maximum value of fundamental? 4 Vs by pi into sin. 4 Vs by pi into sin. What is the RMS value of nth harmonic output? This is 5 star. Very, very, very important. In a single PWM technique, what is the RMS value of fundamental voltage? 2 root 2 by pi into Vs into sin. 2 root 2 by. From these so many times the formulas, the questions are framed. That you have to consider. Then this ratio also you have to consider. Then this is for single PWM technique is applied for full bridge inverter. If single PWM technique is applied for full bridge inverter, and Fourier analysis is this one. If it is single PWM technique is applied for half bridge inverter, if it is asked Fourier analysis of half bridge inverter, in these formulas just replace Vs by Vs by. That is for half bridge inverter. That is, I told already, single PWM technique. Not only single PWM technique is mainly to eliminate the harmonics. But if you use a single PWM technique, the total harmonic distortion is high. At a time, only one harmonic is eliminated. Then to eliminate the nth order harmonic using single PWM technique, what is the pulse width? This is very important. To eliminate the nth order harmonic using single PWM technique, what is the pulse width that is asked? The pulse width equal to 2 pi by n. Pulse width equal to 2 pi by n. To eliminate the nth order harmonic, what is the pulse width? 2 pi by n. This is very important. If you don't have the time to practice all the formulas, better to practice the minimum these models of question. Whatever the models I saw. Here it is asking that what the RMS value of fundamental voltage. Here RMS value of fundamental voltage is given. It is asking that pulse width. Fundamental voltage, how much it is given? 110. From this I calculated the D value. D is not a pulse width. 2D is the pulse width. Then what is the total RMS voltage? This is the RMS fundamental voltage. This is the total RMS voltage. Then 134.72. Then in this case it is asking that what is the RMS value of fundamental. Use this formula. To eliminate nth order half, this is single PWM technique now. Here alpha is nothing but a pulse width. Pulse width is nothing but a 2D. To eliminate the nth order harmonic, what is the pulse width? 2 pi by n, 2 pi by 5. That you have to concept. Yes, sometimes this is the inverter input is DC. This is the inverter output is fundamental voltage. This is the load voltage. Here there is no any series elements here. Load voltage is equal to fundamental output voltage. That is load voltage equal to output voltage of inverter. If they given any series element here, then don't take this voltage equal to this voltage. Why? Voltage is divided now. If you want this voltage into this impedance by total impedance. Understand? Very important observation. Sometimes if there is no any series element, this voltage, output of inverter equal to load voltage. If any series element is present here, output of inverter is not equal to this one because there is some drop here. Then we have to apply like this load voltage calculation. Then what is the multiple pulse width modulation inverter? In a multiple pulse width modulation inverter, we can generate the number of pulses for half cycle is greater than or equal to 2. Those inverters are called multiple pulse width modulated inverter. The idea behind multiple pulse width modulation is if you generate the more number of pulses for half cycle, then the order of harmonics associated with output is increased. That is, if you generate the more number of pulses for half cycle, output consists of only higher order harmonics. Then all the low order harmonics are eliminated. That is the main motive of multiple PWM technique. What is the idea behind the multiple PWM technique? You can generate the more pulses for half cycle. What the advantage? If you generate more pulses for half cycle, all the low order harmonics are eliminated. Output consists of only higher order harmonics. If output consists of only higher order harmonics, there is no problem. Those harmonics can easily filter by using small size filter. That means very important. Multiple PWM technique will eliminate the low order harmonic, but output may consist of higher order harmonics. Those harmonics, no problem. Those harmonics can easily eliminated by using small size filters. But point to remember how to generate the more number of pulses per half cycle. To generate the more number of pulses per half cycle, we have to use the one control circuit. This is the control circuit. Control circuit is having two inputs, triangular wave, square wave. That is the triangular wave is the carrier wave. Reference wave is the depends on the PWM technique. In different PWM technique, different reference wave can use. But for all PWM technique, which is the carrier wave, triangular is the carrier wave. Sir, why triangular is the carrier wave? Point to remember, students. To generate the more number of pulses for half cycle, we have to maintain carrier frequency is very high. That is always carrier frequency must be greater than the reference frequency. Carrier signal frequency must be greater than the reference signal frequency. Then which signal it is possible to maintain the high frequency? Triangular wave. That's why for all the PWM technique, which is the reference wave, triangle. This you see. Type of PWM, which is the reference, which is the carrier. Multiple PWM, square wave or rectangular, triangular is the carrier. That is based on the type of PWM, which wave is changing, reference wave is changing. But any PWM technique, which is the carrier wave, triangular is the carrier wave. Then in this case, all this not required. Mainly you have to concentrate what is the number of pulses for half cycle. In a multiple PWM technique, this formula is important. In multiple PWM technique, what is the number of pulses for half cycle equal to Fc by 2Fr? Direct formula you have to remember. In multiple PWM technique, the number of pulses for half cycle equal to Fc by 2Fr. What is the modulation index? Modulation index equal to Vr by Vc. Once you know the modulation index, how to calculate the each pulse width? This formulas mainly how to consider. In a multiple PWM technique, what is the RMS value of output voltage? Vs into square root n into each pulse width by pi. Output consists of which order harmonic? 2n plus or minus 1 half. But point to remember, students, modulation index is less than 1 is preferable. Modulation index less than 1 is preferable practically. Modulation index greater than 1 is not preferable practically. If you use the modulation index greater than 1, output consists of low order harmonic. If you use the modulation index less than 1, output consists of higher order harmonics. If the output consists of higher order harmonics, no problem. Then better to practice these models of question. Here in this problem, it is asking that you have to calculate the RMS output voltage of multiple PWM. This is the RMS output voltage. Let us assume that this multiple PWM is applied for full bridge inverter. Here I am explaining for full bridge. If the same question is asked for a half bridge inverter, replace Vs by 2 students. Simply remember. Once I given only formulas for half bridge inverter, I am not giving any formulas for full bridge inverter. Sorry. Once I am giving only formulas for full bridge inverter, I am not giving formulas for half bridge inverter. If you have to write the by your own, just replace Vs by Vs by. Here if they are given RMS output voltage, how many number of pulses per half cycle it is asked. Here reference voltage is given, carrier voltage is given, carrier signal frequency, reference signal frequency is given. What the modulation index VR by VC? What how many number of pulses for half cycle FC by 2FR? Each pulse width that you have to calculate. That's right. Each pulse width 1 minus VR by VC into pi by L that you have to concentrate. Then what the Fourier analysis of multiple PWM technique? These formulas are not that much of important. Mainly how to concentrate gamma formula. Gamma equal to pi minus. This is constant. Pi minus 2d by n plus 1 plus d by n. Then for different. This is for single PWM. This is the Fourier analysis of for any number of pulses. For any number of pulses, this output. In this, you have to substitute n equal to 1 for 2 pulses, n equal to for sorry, n equal to 1 for single PWM technique, n equal to for 2 pulse PWM technique, n equal to 3 for 3 pulse PWM. This formula is the generalized formula to write for any number of pulses for half cycle. But we don't expect this formula already given for a single pulse with. And this problem you have to practice. But the RMS output voltage and with output power it is asking. Output power is V naught RMS. If modulation index less than 1, output consists of higher order harmonics, hence practically modulation index than 1 is preferable. If modulation index greater than or equal to 1, output consists of low order harmonics, hence it is not preferable. Next, sinusoidal PWM technique. In sinusoidal PWM technique, which is the carrier wave? Triangular is high. Reference wave is sinusoidal. But point to remember, in multiple PWM technique, whatever the output pulses we are getting in multiple PWM technique, these output pulses are having the equal pulse width. But in the case of sinusoidal PWM technique, the output pulses are not equal, not identical, because the magnitude of the sinusoidal waveform is always changing. The reference wave is changing. The output pulses are not identical, that is, they are having the variable pulse width of pulses. The width of the pulses varies in accordance with the magnitude of sinusoidal waveform. How the width of the pulses are changing? Magnitude of sinusoidal waveform, that is the reference wave. Here, two conditions are there. If peak of carrier coincides with zero of reference, peak of carrier coincide. This is the peak of carrier. This is the zero of reference is coincide. How many number of pulses for half cycle? FC by 2FR. The number of this all these derivation not important. How many number of pulses for half cycle you have to remember? Zero of carrier, zero of reference is coincide. How many number of pulses for half cycle? The number of pulses for half cycle equal to FC by 2FR minus 1. FC by 2FR minus 1. That you have to concentrate. Then there is unipolar switching. In sinusoidal again there is unipolar and bipolar. In unipolar switching, one half cycle completely positive pulses, another half cycle completely negative pulses. This is called unipolar switching. Bipolar switching means every half cycle positive, negative, positive, negative, positive, negative. That is called bipolar switching. It may be unipolar switching or bipolar switching. What is the maximum value of fundamental voltage? MVS. Maximum value of fundamental voltage is M, where M is the modulation index. What the RM, this is very important for. What the RMS value of fundamental output voltage? MVS by root 2. This is for full bridge inverter. If unipolar or bipolar switching is applied for full bridge inverter. If it is applied for half bridge in before this, this is the distortion factor formula. This is a total harmonic distortion formula. If output voltage of unipolar or bipolar switching for half bridge inverter means previously it is MVS now. It is MVS now, but it is MVS by 2. Just replace VS by VS by 2. MVS by 2 is MVS by 2. This is for which inverter? Half bridge inverter. Then what is the frequency modulation index that you have to concentrate? Then if frequency modulation index is given, what is the order of harmonics at output side? The frequency modulation index is given, what is the order of harmonics at output side? This is very important. This is a repeated question in gate exam. If sinusoidal PWM technique is applied for 3-phase bridge inverter, RMS value of fundamental line voltage formula. Root 3 by 2 root 2 into MVS. RMS value of fundamental line, peak value of fundamental line voltage. This is the RMS na peak. How to get peak value? Once you know the RMS, how to get the peak value? Multiply into root 2. If you multiply with root 2, root 2 cancel. Then root 3 by 2 into MVS. This is the RMS value of fundamental AC line voltage. This is the peak value of fundamental line voltage. This is for the, where M is the modulation index. This problem we have to practice with respect to multiple PWM technique. If the question is asked, how to solve this one, and this problem also you have to practice. This problem also you have to practice. I given the solution. This is also question based on the. This question is based on. This is single PWM technique, single phase full bridge inverter, fundamental value of output. This is unipolar switching, bipolar. That is sinusoidal PWM technique. Unipolar bipolar switching it is given means sinusoidal PWM technique you have to apply. This problem you have to practice. And one more topic with respect to inverter. This is the final concept with respect to inverter. Three-phase inverters. Three-phase inverters are nothing but a six-step inverters. It is a combination of three half-bridge inverter. It is a combination of three half-bridge inverter. How many switches and how many diodes? Six switches and six diodes. But these three-phase bridge inverters are operated in two modes. One is 180-degree mode, another one is 120-degree mode. This is the three-phase voltage source inverters. The voltage source inverter, it requires feedback diodes also. This is a three-phase current source inverter. It does not require any feedback diodes. It is having only switches. Three-phase current source inverter is only switches because current source inverter no need of feedback diodes. What is the purpose of using capacitor bank? A three-phase capacitor bank is used to reduce the voltage spikes. In three-phase, this capacitor bank is used to reduce the voltage spikes. If there is more voltage spike, there is short circuit at the terminals. That's why to overcome that problems we are using the three-phase capacitor bank. A three-phase full bridge inverter is, this is also very important. In general, a very high power induction motor will have this property, having less leakage. That's why current source inverters are more favorable for high power induction motor drives. For high power induction motor drives, it is why? Because in high power induction motor drives only the leakage impedance is less. Three-phase inverters are operated in 180-degree mode and 120-degree mode. What exactly 180-degree mode? This problem also you have to question you have to practice. This is a matching question. Then what do you mean by 180-degree mode? In 180-degree mode, the sequence of conduction of device are like this: 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6, 5, 6, 1, 6, 1. That is 180-degree mode means each device is allowed to conduct 180 degrees. Each switch is triggered at 60-degree interval. Each device will conduct 180 degrees, but each switch is triggered at a 60-degree interval. That is nothing but a 180-degree mode of operation. This final conclusion points that mainly you have to concentrate. This operation, all this not required. Mainly concentrate. These are the waveforms. In 180-degree mode of operation, this is the phase voltage waveform. Phase voltage waveform is stepped waveform. Line voltage waveform is quasi-square wave. Line voltage waveform is quasi-square wave. These points are important. In 180-degree mode of operation, each switch 180 degrees it will conduct. Three switches are conducted at a time. Each switch is triggered at 60-degree interval. What is the shape of the phase voltage? What is the maximum amplitude of phase voltage? What is the shape of the line voltage? What is the maximum amplitude of line voltage? What is the phase sequence between what is the phase difference between two sequential SCRs? Either top or bottom is 120 degrees. And in 180-degree mode, there is a possibility of shoot-through fault. Shoot-through fault means a short circuit fall through source. Shoot-through fault means a short circuit fall through source. In 180-degree mode, there is a possibility of shoot-through fault. Then what is the analysis of line and phase voltage of 180-degree? This is very, very important 5-star. Already 2 marks questions are framed in GATE exam based on this analysis. RMS value of line voltage formula important. RMS value of phase voltage formula is important. All these are 180-degree modes. What is the phase current formula? What is the average value of switch current or thyristor current formula? What is the RMS value of switch current formula? What is the three-phase load? Many times the questions are asked based on three-phase load power. To solve this three-phase load power, you have to find I phase. To find I phase, you have to know the V phase also. So 180-degree mode. What is the RMS value of line voltage? RMS value of phase voltage. Very important, students. What is the RMS value of phase current? What is the average value of each switch current? What is the RMS value of each switch current? Three-phase load power. This is for 180-degree. If you apply the Fourier analysis for 180-degree mode, this is the instantaneous voltage of phase voltage. But this is not important. This you have to remember. In 180-degree mode, what is the maximum value of nth harmonic phase voltage? Maximum value of fundamental phase voltage. RMS value of nth harmonic phase voltage. RMS value of fundamental phase voltage. Very, very important. If you apply the Fourier analysis for 180-degree mode, this no need to remember. This instantaneous values no need to remember, sir. This only you have to remember. This is very important. This is the phase related formulas of 180-degree mode. This no need to remember. This is the line related formulas of 180-degree. Line related formulas of 180-degree. what is the maximum value of nth harmonic line voltage, what is the maximum value of fundamental line voltage, what is the RMS value of nth harmonic line voltage, what is the RMS value of fundamental line voltage. This you have to calculate. And this is very important for our students. Directive formulas are also asking in GATE exam. This is based on Fourier analysis. In 180-degree mode, what is the switch utilization factor? What is the switch utilization factor? That is 33.33%. At a time, 3 switches are conducted. And this problem you have to practice with respect to 180-degree mode of operation. 180-degree mode, what the phase current, what the RMS value of switch current, what the 3-phase load power. All the formulas that I given, please go through this one. Next, 120-degree mode of operation. In 120-degree mode, what is the sequence? 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 1. But in 180-degree mode, at a time 3 switches. But in 120-degree mode, at a time only 2 switches are conducting. Each switch is conducts 120. Here also 60-degree interval. But this operation, all this not important. Final conclusion points mainly you have to consider. These are the waveforms in 120-degree mode. In 120-degree mode, as compared to 180-degree mode, the line voltage and phase voltage waveforms are reversed. Here phase voltage is quasi square wave, line voltage is stepped. In 180-degree mode, phase is stepped, line is quasi. But here phase is quasi, line is stepped waveforms. Then conduction angle of each switch is 120 degrees. 2 switches are conducting at a time. Each switch is triggered at 60-degree interval. Shape of the phase voltage is quasi square wave. Shape of the line voltage is 3-stepped waveform. What the maximum amplitude of the line voltage is Vs. What the maximum amplitude of phase voltage is Vs by 2. What the phase difference between two sequential SCRs is 120 degrees. That you have to consider. But here there is no possibility of shoot through fault. In 120-degree mode, there is no possibility of shoot through fault. And this is the line and phase voltage analysis. Like in 180-degree mode, what are the formulas are given? Like this, here also you have to concentrate what the RMS value of phase voltage in the case of 120-degree mode, what the RMS value of load current, what the RMS value of line voltage. Every formula is important. Phase voltage 0.408 Vs, phase current I phase equal to V phase by R. This phase current is also called load current. Phase current and load currents are equal. RMS value of load voltage, RMS value of line voltage, that is 0.707 Vs. Then what is the average value of switch current, RMS value of switch current, average switch current or thyristor. Here switch is, thyristor also is used as a switch now. That's why switch current is asked or thyristor current is asked. Same formulas we have to apply. 3-phase load powers. 3-phase load power. And the Fourier analysis of 120-degree mode. Fourier analysis for phase voltage. This no need to remember. Directly remember this one. This is the direct formulas. Maximum it is asking. What the maximum value of nth harmonic phase voltage in 120? This is 120-degree mode related. First starting I given 180-degree mode. This is 120-degree mode phase voltage. What the maximum value of fundamental phase voltage in 120-degree mode? What the RMS value of nth harmonic phase voltage? What the RMS value of fundamental phase voltage in 120-degree mode? And this is the line voltage analysis. This is the line voltage analysis. Mainly these formulas are important. This is the line voltage formula. What is the maximum value of nth harmonic line voltage? That is 3 Vs by n pi. What is the maximum value of fundamental line voltage? 3 Vs by pi. RMS value of nth harmonic line voltage? 3 Vs by root 2 n pi. RMS here phase RMS value, fundamental value. Even line also RMS value, fundamental value. That also you have to consider. Maximum value, fundamental value. RMS value, fundamental value. These formulas mainly you have to consider. And what is the switch utilization factor? 28.9%. But in the case of 180-degree mode, the switch utilization factor is 33.33%, where at a time 3 switches are conducting, but here at a time only 2 switches are conducting. And this problem you have to practice for 120-degree mode of operation. This problem you have to practice for 120-degree mode of operation. All the formulas that I given, apply those formulas, you try to solve this one. This is very important. Maximum it is asking the 3-phase load power. Once you know the I phase, how to calculate the 3-phase load power? 3 into I phase square into R for phase 1. 3 into I phase square into R for phase. That formula also you have to practice. But this is some important points. In both 180-degree mode and 120-degree mode, phase and line voltage does not consist of triplet harmonics. In phase and line, there is no triplet harmonics in 180-degree mode and 120-degree mode. But in 180-degree mode, only pole voltage in the sense switch voltages consist of triplet. That is where the triplet harmonics are present. In 180-degree mode, only pole voltages. Remaining, there is no any triplet harmonics. 180-degree mode has high switch utilization factor. For same supply and load using 180-degree mode, more power is delivered to the load as compared. That is, in which mode more power is delivered to the load? 180-degree mode. Why? At a time 3 switches are conducting, but in 120-degree mode only 2 switches are conducting. That is about the detailed explanation and important observations from module 4 inverter, that is the DC to AC. With this, inverters concepts are complete. This is about the session. Thank you.